All right, let's get started. So, welcome to Lecture 5 of the SNAPP summer course on Stein's method and queuing approximations. At this point, you all know the drill, so videos and notes go up on the website after each lecture. So, Anton, take it away.
Okay, perfect. Good morning, everyone. A few things to say. Maybe let's start with a quick recap, and then we'll talk about what we're doing today. So last week, really the full week was um, designed to give you from A to Z the full formula for the generator approach. And I just want to recall the main ingredients. So I have a diffusion process, y of t. Of course, we said we're never going to really care about the process as much as we care about the stationary distribution. And I have a CTMC, okay, x of t. And we use the infinite server Q, and the stationary distribution is given by x. But I want to mention that what we did holds for any CTMC, and in fact, it holds for DTMCs as well. Stationary distribution X. Step one, well, for us, step one was really to derive or Taylor expand the Markov chain generator and derive the diffusion. And after we have that, we're going to look at the Poisson equation. In the Stein method community, it's called the Stein equation, by the way. But I think that it's 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 fair to make the following distinction. When you're dealing with a normal limiting distribution or a Poisson limiting distribution, these are examples or random variables for which Stein's method has been applied over and over and over again. It's really fair to call it the Stein equation, okay? But when we're dealing with these diffusion processes, some exotic diffusion where nobody in the Stein method community has even ever heard of it, right? I think it's more fair to call it the Poisson equation because the Poisson equation is associated with these diffusion processes. Anyway, some useless opinion that doesn't really change things, but it's just good for context. Okay, so we start with the Poisson equation. We set x, little x to be the stationary distribution and take expected values. And we get that this distance between x and y can be written in terms of the generator difference. And I'm doing this recap also in case anybody's starting to watch the video from this one missing last week will not be very lost. Okay, and this of course equals 0. Of course, we have to verify that by the BAR. We have to verify the regularity conditions. And then we had these derivative or sometimes called gradient or sometimes called Stein factor bounds on the norm of the second and third derivative. Well, we may also need higher order ones, but typically it's second and third. And then 3, it's moment bounds. Of course, 2 and 3 are interchangeable. You don't have to do one before the other. So expected value, let's say absolute value of x, less than or equal to something, usually some constant. Okay, and then we're done. Now today we're gonna look at this a different way. And today I want to introduce something called the pre-limit approach. And yeah, you know what? Let me, before I talk about the pre-limit approach, a little detour. I just want to make a connection between, say, the Poisson equation and the drift method, or using Lyapunov functions that we've talked about originally. So if we even like don't assume that the process is stable, that the if we don't assume that the diffusion process is stable, and we want to show this, right? Would we do this? Well, we would find some kind of test function such that it would have a negative drift towards the origin outside of some compact set. Now, what was special about the Poisson equation, so let me do it over here, is that the solution to the Poisson equation is known, or just has this probabilistic form. It's the expected value starting in some initial condition minus expected value h of y dt. Okay, so let me take h of x to be the indicator that x is outside of some compact set around the origin. Okay, then um, you know, well, no, actually, I'm sorry. Ignore what I've been saying. Ignore this part. Wasn't sound. Sorry for wasting time. Okay, ignore that part. I'm going to come back to it when we talk about fluid approximations. That'll be much better then. Sorry about that. So, okay, coming back today, the prelimit approach. Number one, let's carry out the same steps. So we're given the Markov chain and a diffusion stationary distribution. And now we're going to start with the Poisson equation, which is going to be not the Poisson equation associated to the diffusion, rather the Poisson equation associated to the Markov chain. And I'm going to use x sub q. I want to recall, for example, our notation from last week, where really the Markov chain was some q length process. And we renormalized it. So x is the normalized version, but I keep writing x sub q to make it clear that x is really a function of some integer, okay, or some countable state space value. So in this case, say q is going to be on the non-negative integers, and then x sub q can be some recentered version, square root of r, for example. Okay. Now this will hold, let me not write the state space yet. It'll hold on some grid. What we want to do is to take little x sub q to be the diffusion stationary distribution and take expected values. And then what do we get? We get a similar picture to what we had up above. G f sub h of y minus gy f sub h of y. Now, again, this would be 0 using the BAR. And what is the advantage? Suppose what I'm writing down is sound, okay? What is the advantage of looking at the generator difference this way? Well, if assuming things work the same way as they did upstairs, right? The generator difference would depend on, let's say, second, third, and fourth order terms in the Taylor expansion of the Markov chain generator. Notably, it would depend on the derivatives of this potential for the Markov chain. And then what we would get is step two, Stein factor bounds for the Markov chain triple prime, and then moment bounds for the diffusion. For example, the first moment of the diffusion is bounded by something. Okay. Now, assuming I'm going to poke holes in this now, but assuming we can do all of this, assuming this agenda holds even, what is the merit or what is the benefit of doing it this way? Well, the benefit is actually, I would say maybe both in two and three, but really the benefit is in two. Because sometimes it may be the case that getting these derivative or gradient bounds is too complicated. It's too difficult of a task. We don't know how to do it. We've thrown everything we could at it, and we don't know how to bound these derivatives. It may be the case that the Stein factors for the original Markov chain are more tractable or it's easier to bound them. Okay. And of course, an example is king to illustrate all of this. And at the end of today, probably next class, we're going to talk about an example using the infinite server queue. It's going to make this very clear. But the focus of today is really to make this three-step approach precise or mathematically correct, okay, so that we can use it later on. And now I keep saying like there's something wrong with this, there's something wrong with this. Let me show you what's wrong with this. Okay. And of course, I've made it a point to say at the start that the Markov chain has a countable support, but the diffusion has an uncountable support. So this step is illegal. We're not allowed to do this. Why? First of all, your test function h, for the purposes of the Poisson equation, the test function h is only defined on a grid. When I say grid, I mean I'm referring to this. Okay. Um, but then you say, okay, well, the test function is up to us to choose. We could, of course, extend it to the entire real line in any way we please. That's not an issue. I agree with you. Okay, so I say, okay, fine. We can extend the definition of the right-hand side to the real line. There's no problem there. But then the left-hand side, again, only depends on the grid or only defined on the grid. And you can say, well, let's extend that too. And I say, okay, let's try to extend that. So the first thing I want to show you right now is that this is not a trivial problem. That's what I want to convince you, that this extension is not immediately trivial. Okay, so left-hand side, we have the generator. Now we do special case, the infinite server queue. This is just a reminder, we had lambda, f sub h, x of q plus delta, and delta was the scaling constant. It's equal to 1 over square root over r. And we had the death rate, and the death rate, I want to remind you, is mu x sub q over delta minus r, plus r, not minus r, plus r. And we had x sub q minus delta x sub q. By the way, you may have noticed I'm using a capital F sub h to denote the Poisson equation solution. I'm doing this, so I want to make a distinction between the diffusion Poisson equation, for which I use a lowercase f, and then this is the Markov chain Poisson equation. Okay, so this is the left-hand side. And now you can see if we want to extend it, we need to do two things. Need two things for an extension. Number one, extend the Poisson equation solution to the entire continuum. Okay, and you can say, okay, well, that's fine. I can do that. There's infinitely many extensions. I can make it piecewise constant, or I can make it linear in between the grid points. And then step number two, maybe this is maybe a little bit less obvious, but the generator, right? It doesn't just depend on the function that it's acting on. It also depends on the transition rates from each state in the state space. So we have to extend the transition rates. Right. What are the transition rates in this case? We have one transition rate lambda, and we have one transition rate mu times x sub q over delta plus r. So lambda is a constant. It actually is already defined everywhere. Great. No headache there. What do we want to extend the death rate to? Well, if you look at this, I think it's pretty, there's one very natural candidate. Let's say we want to do x sub q plus r times mu. We want to extend that to the just linear function, right? That's very natural. And um, yeah, I don't have any reason not to do it like this. I just want to make a little caveat. Remember, x sub q, this is delta q minus r for q bigger than or equal to 0. Or x sub q, this is at least as big as x sub 0, which is delta times 0 minus r. This is negative delta r. And if we remember that delta is 1 over square root of r, this thing is, you can look at it as negative 1 over delta or negative square root of r. Okay, so just some a little bit of algebra. Well, what does that mean? It means that x sub q is bigger than or equal to negative delta r, and therefore the death rate is bigger than or equal to the death rate at 0, and this is just going to be 0. So really my extension should be to mu x over delta plus r maximum 0, because I don't want a negative transition rate. I'm not going to dwell too much on this. This is a little technicality that you just have to be aware of when you do this. It's not a big deal, okay? But I don't want to dwell on this part too much. Anyway, so we do the extensions. So we said we trivially can extend the right-hand side. We can extend the left-hand side, right? There's a natural extension of the transition rates, and we can use any extension we want for the Poisson equation solution. And therefore, boom, we've extended both left-hand side and right-hand side to the real line. What is the problem? Well, the problem is that G, whatever our extension is, we want it to still take the same values at these grid points. So this will be satisfied, but G, let me just say that the extended version, G sub F. So I use the tilde to denote the extended left-hand side, need not be true. I'm not saying it's not I'm not saying it's not true. Need not be true for all x in R. Okay, so in other words, just because you've extended both sides doesn't mean that the Poisson equation continues to hold everywhere. And that's really the key point. So we need to do something a little bit more sophisticated in order to extend the whole Poisson equation to the real line, not just extending the individual components of it. And this is what we're going to do today. Okay. Just before I dive into a lot of like very technical content, I just want to put this in perspective. So when people use Stein's method, we can have in Stein's method, we can have, say, a continuous versus continuous comparison. For example, if we have the CLT, so xi or IID sum x, and y is a normal 0, 1, and we make an assumption that these x's are defined on the entire real line, for example, they have uncountable support. Therefore, the sum of the xi minus the mean over square root of n times the standard deviation versus a normal 0, 1. So this is what I mean by continuous versus continuous comparison. And that's all fine because we can use the Poisson equation for the normal. The Poisson equation is defined the continuum. This thing doesn't matter where it's defined because already the Poisson equation for the normal is defined the continuum. We plug in the value, we plug in this random variable into the Poisson equation and we're good to go. And this was what we did last week. When we do discrete versus discrete approximation, again, we have the same concept. We're going to use the Poisson equation for one discrete variable. For example, it could be the Poisson distribution. And assuming that the other variable which we're comparing it against also has the same support, we don't really have an issue. So we use the discrete Poisson equation and we don't have this issue of needing to extend the Poisson equation. So now the third case really is continuous versus discrete random variable. And this was our example last class. We had the m infinity, and we had the Ornstein-Uhlenbeck, which corresponded to our normal 0, 1. We start from the Poisson equation of the continuous one, and then we can plug in the discrete valued random variable, no problem. But really the gap, what we're doing today, the gap it's filling is if we start with a discrete Poisson equation and we're trying to plug in the continuous random variable, there we're going to run into an issue. Okay, so conceptually, this is the gap we're filling today. And to the best of my knowledge, I didn't see this stuff implemented anywhere else. And yeah, let's start to talk about it. So to start our conversation, I want to talk a little bit of a detour on function interpolation. This is something you would have covered in your numerical analysis class if you took it at the undergraduate level. Let's talk about this. So given a function, delta, so a function, so delta, again, is some scaling constant. And we have a function on the integers. And I'm going to just refer to this as the grid. This is a grid, right? We now construct an extension. AF such that, and the key property is, of course, such that A, or the derivative of this extended value, so this is the derivative of order little a, is somehow approximated or somehow corresponds to the finite differences of the function. Okay, where delta f x sub k is the forward difference. And I'm going to switch to using x sub k. This is delta times k. It's going to be on the grid. So k is going to be the integer component, or it's going to be the grid point corresponding to x sub k. And why do I want to preserve this? We'll see in a second. But if I, let's say, if I don't demand this property, it's trivial to extend things. But our extensions are not going to do us any good. This is really the property we want. And you can see that this is going to say, well, in the generator difference, we have these derivatives of the potential function. we want them to correspond to the finite differences of the Markov chain potential. Okay. So how are we going to extend this? And we're going to do it as follows. So this is point 0. This is the point x sub 1, which is just delta, the first grid point. X sub 2, this is 2 delta, etc. And we can have points on the left as well. And say we are given the values of our grid valued function. What are we going to do? We're going to interpolate them somehow. Okay, such that the red point are the values of the function, and the blue curve is my interpolated function. And the way we're going to do that is we're going to use some basis functions. So I'm going to call this p sub 0 of x. I'm going to call this p sub 1 of x. This would be p sub 2 of x. So I'm going to right now construct a basis function. In interpolation, a common choice of a basis function, for example, is this tenth function. And you would have these triangular tenth functions going everywhere. We're going to use something a little bit smoother. We're going to use Hermite spline. But let me define these p sub k's. For k, we're going to let p be a polynomial in x such that now we want our basis functions, or we want these splines, another way to call them, or spline, we want it to satisfy the following things. First of all, I eventually want my blue function to be differentiable or regular. And if I define my blue function in terms of these piecewise, or if I define my blue function as a pasting of these functions which are defined only on the interval, I better make sure that at the boundary points where these functions meet, I have smoothness. Okay, I already know that, so that if I choose p to be a polynomial, I already have smoothness within the interval. But now I need smoothness at the points where these things get glued together. So first of all, my polynomial should take the same value as the function at the grid points. Okay, number one. Number two, p sub k at the right endpoint where this polynomial is defined, I should also have this agreement with my original function. Now we're talking about smoothness. The derivative of p sub k at the, right, so we have, let's say this is p sub k. It'll be defined on this interval from 0 to delta. And now we have that the derivative at the left endpoint must equal delta minus 1/2 delta squared plus 1/3 delta cubed f of x sub k. Okay, and same thing on the right point. This is that the derivative, I'll write this down and explain it to you in a second. Of x k plus 1. Okay, so what this is saying is that basically if I take p sub 0 and I look at p sub 0 at the point x1, so p sub 0 at this point, right? I'm going to, first of all, fix the value of the derivative at this point, and I want it to be some function of my original or some function of the finite differences of the original grid valued function. Now, why am I using this complicated looking expression here? This is really an estimate of, let's say, f prime of x sub k plus 1. So if I were to write just delta f of xk plus 1, you would recognize that this is the forward difference, and this thing approximates the derivative of my function, right? Now, this thing looks like an upgraded or a more complicated version of the forward difference. And what it does is this is like a higher order approximation for the first derivative. But what I want you to think about is that this is an approximation of the, let's say, first derivative of this function at the grid, should the function be continuous, of course. So I'm going to say that my polynomial at the right endpoint is fixed to be this constant. And this condition will basically say that p sub 1 at the left point must correspond with p sub 0 at the right point. So that's what these two conditions do, the first derivative. Let me pause and ask if there are any questions, because I don't think I'm doing the clearest job possible here.
So, I missed a part of this explanation, but so it's the idea that the polynomial is sort of like smoothly interpolating f is very clear. Um, could you summarize the properties that this setting employs in terms of like things that are preserved? So it's clear that we preserve the function values at the xk.
Yeah.
It's clear that the derivatives match at each dot.
Yeah.
Is there is there something important to understand about what properties are sort of ensured by this specific setting with the delta squared and delta cubed, like third derivative matching or something like this?
Yeah. Yes. So let me just say that I wanted I will, at the end of it all, I will summarize the main properties that I want this interpolant to satisfy.
Cool. Then maybe we
But
should.
to give you again, to give you basically a preview, and I think this may be related to Yang's question, right? Given the red function f, given it's defined only on the grid, it need not it need not be differentiable. In fact, if it's only defined on the grid, the derivatives will not exist. So what is our next best thing when it comes, what are derivatives? Derivatives are just a measure of how the function changes. So when we have a function that's defined on grid points only, we don't have derivatives, but we do have these forward differences. And this is literally the measure of how the function changes from one grid point to the other. So when we're constructing our blue interpolant, um, we want its rate of change, its derivatives, to mimic as much as possible the the differences of the original red function. Okay, and I'm going to write down some more conditions, because this basically says that the interpolant has to coincide with the function on the grid points. This second set of conditions is the first derivative must equal something, okay? And what I said, and I'm going to reiterate again, if in what I've circled, I had only written just delta, no delta minus delta squared plus delta cubed, just delta. I think this would have been clearer to people that's saying that, okay, I really want this to look like the forward difference of my function. Now, for reasons that will not become clear at this talk, but I'll say why. I actually want to use a higher order approximation of the derivative of f. Okay, so let me do a quick detour.
So the idea is that the forward difference of the forward difference will roughly match the second derivative, something like this.
Yeah, exactly. So let's say if f, let's say was in C infinity, then delta f is like the first derivative plus order delta squared. So the error of the forward difference is like delta squared. But the error of what I've written down, delta minus 1/2 delta squared plus 1/3 delta cubed, applied to f. This is actually like f prime of x plus order delta to the power of fourth. So I really want, yeah, this is the level of detail. I'm not going to get into why it's necessary, but unless people ask for it. Eva.
I just wanted to check that when you say delta squared, does that mean that the operator delta is applied twice? And what would that look like?
So delta is a constant. In this case, delta.
Ah,
Little delta, capital delta. Yes, yes, yes. Exactly. So I think maybe this is useful. Um, so we have a forward difference, and that is exactly plus delta minus f of x sub k. We have delta squared, which is just a composition. Okay. This is delta applied to delta f of x sub k, which is delta of f of x sub k minus f of, oops, sorry, plus delta minus f of x sub k, which is going to be f of x sub k
oh,
plus 2, but now it's 2 delta minus 2 f of x sub k plus delta plus f of x sub k. Okay. And this Taylor expansion is basically f double prime. This is like the second, if the function were differentiable, this would be like the second derivative plus, I think it's ordered delta cubed. And the delta cubed, this is like delta cubed times f triple prime. That's some function. Okay. So maybe this will convince people, although really it's not quite the point. Kind of hope you will believe me on this. Delta squared plus 1/3 delta cubed applied to some function. This is basically, so the reason is, just look at this term. I am looking at the first forward difference, and the forward difference will be like f, this thing will be like f prime of x sub k plus 1/2 delta squared f double prime of x sub k plus delta cubed f triple prime something. Okay, that is the expansion of the green term. So when I am subtracting 1/2 of the second order difference, what I'm really targeting is I'm targeting this term and I'm getting rid of it I'm trying to get rid of it using this 1/2 of delta squared. Okay. And the same logic, basically, you can get rid of arbitrarily many terms and you can have an arbitrarily accurate approximation of the first derivative. Okay. So that's for that, but I think it's important to give people practice with what do I mean by this delta squared?
sorry, one other thing. In the green, I think this is part of what's been tripping me up. The F prime, there's supposed to be a delta after that, right?
You're right. I'm sorry. You're right.
No, 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 that totally makes sense. Thank you so much for explaining. I really appreciate it.
Yep. Perfect. I think I was confusing a lot of people. Okay. So one more question. Why must it exist? So we're not assuming f prime exists. We're saying if it were to exist, this is what our approximation would look like. And here I want to make it clear that all we need to exist is the grid valued function. So the value at these grid points. Our interpolation scheme, that's constructive. It's going to be sufficiently differentiable just by construction. Okay, so I have this condition on the value of the function, the condition on the first derivative, and as you would imagine, I want to have some conditions on the second and third derivatives. So let me just write this down for the sake of having a record. This is going to be delta squared minus delta cubed f of x sub k. And this is basically saying I want this to be a higher order approximation of the second derivative. At the right endpoint, x sub k plus 1, at the right endpoint, I want this thing to be the same. F of x sub k plus 1. And the third derivatives, as far as those are concerned, I want this to be corresponding to the third order forward difference. Plus 1. This is the third order forward difference. Okay. So let's count with me, okay? How many equations do we have? 1, 2, 3, 4, and then 4 more on the other page. So I have eight linear equations. Therefore, I need 8 variables. And what is the lowest order polynomial with 8 degrees of freedom? That is a 7th order polynomial. Okay, so this is for convenience, gamma sub k. So gamma sub k is basically I look at the value x, I subtract away delta k, and I divide by delta. Think of this as being some linear function of x. Then p of x then the above equations are solved by p sub k. And this is one of those things, I'm going to write it out once, we're going to see it once, but we're not going to come back to using it very much. I just want a record. Cubed f of delta k. So here I'm using delta k. This is x sub k. The same thing. Plus 1/2 gamma of x squared. Delta squared minus delta cubed. So what I'm writing down, this is literally obtained by solving these 8 linear equations. And this is where it gets funky. 23 over 3, gamma the fourth, delta 4, f of delta k. Let me be consistent and do it this way. But these long pauses usually give the audience a question to think and see if they get any questions of their own. Little typo. Oh no, not a typo. Not a typo. Minus 55 over 3, gamma. So this was done in the days before ChatGPT. There were symbolic packages, of course, but I figured that doing this by hand is still quicker than trying to figure out how to use a symbolic package. Nowadays, you just ask ChatGPT this. Okay, so what I want to highlight is number 1. This is a polynomial in x because the gamma is we can think of gamma as just x, okay? It's a linear function in x modulo some centering and scaling. So this is the linear term. This is the quadratic term. This is the cubic term, quartic term, and 5th order term, 6th order term, 7th order term. what about this f of delta k? So I think really maybe take the highest order term and talk about it there. If I want to understand what values of my original grid valued function does p sub k depend on, I have to look at the fourth order difference. And for reference, the fourth order difference is, so this is Pascal's triangle, 1, 4, 6, 4, 1. So this would be f of delta k plus 4 minus 4f of delta k plus 3 plus 6f of delta k plus 2, f of delta k plus 1, and this is f of delta k. Okay, so in other words, in order for me to have a p sub k well defined, I'm going to use information about the value at delta k plus 1, 2, 3, 4, 5. So 4. So in other words, I have 1, 2, 3, 4. I need 5 red points in order to define this polynomial. Okay. And you will see, like, why 5? 5 is an arbitrary number. And the reason was that I basically wanted this thing, the entire spline to be C3. And that's why I needed to match up to the third derivatives. Anyway, so easy to verify. This is just using using this form of this polynomial, that if I look at the eighth derivative of order A of this polynomial at the left-hand point, p sub k, this is equal to the derivative of p sub k minus 1. So the basis function right to the left of it at the value of x sub k as well, for a between 0 and 3 for any point on the grid. Okay, what does this mean? This means that there's smoothness at the points where they intersect. Okay, so let k of x be x over delta. So k is the closest integer from the left to x. K of x is the closest integer from the left. We define a f of x as the polynomial, okay, the polynomial at x, but which k are we using? We're always using the k to the leftmost point. Let me draw this on a picture. So taking this to the next page. So again, I have my grid. This is the point 0. This is x sub 1, x sub 2, x sub minus 1. I have my function. And over here, so if I look at a f of x, where k of x is the leftmost integer or grid point, a is the polynomial based on the leftmost integer point. So here I'm using p sub 0, because for any x in this region, k of x is going to be 0. The leftmost grid point is 0. Here I would be using p sub 1 of x. Here I would be using p sub 2 of x. So, right, this form basically says whatever interval you're on, you're going to use the polynomial that is corresponding to the left grid point. Okay, and based on our complicated construction, we basically enforce that A is a C3 function, and actually dA exists for all A bigger than or equal to 0, and for all as long as we are not on the grid points. Okay, so in other words, I've only ensured that at the grid points these things can be pasted smoothly to the third order. For higher orders, they're not going to, they're the value of P, the value of the fourth derivative of P naught and the value of the fourth derivative of P1 at the grid points is not going to coincide. Although in hindsight, I should have made that work too. Anyway, so it's C3, but within the interval, it's just a polynomial of seventh order. And so it's infinitely differentiable. Okay, so almost there with the properties. Okay, given any function, we have defined an interpolant, a sub f, using from this very low-level definition. In numerical analysis, just as a in the terminology of numerical analysis, we have P sub k these are called our seventh order basis functions or seventh order polynomial basis functions. And P sub k is called a Hermite spline. Okay, this is just to connect things for people with numerical analysis background. Okay, so now we're going to be coming out of the weeds and discussing things at a higher level. And before I do that, are there any clarifications or any questions about what we've done so far? I know it was tedious, but hopefully you'll believe what I'm doing for you. Okay. The most important property we want, and eventually we're going to get there, is that the derivative of the function is bounded from above by some constant times delta to the power of negative a times f of k of x plus something. Okay, I'll be more precise, but basically we want this property to be satisfied. I don't really need the derivatives of the interpolant to correspond exactly to the respective finite differences, but I do want the derivatives to be bounded by the finite differences in some sense. Okay, so that's what I'm chasing. And this can be verified directly. Directly using pk of x form. All right. I guess since I'm going to leave this part here as it is, let me fill in this. Let me make this rigorous. I've got times maximum. If this part is going to confuse you, just hold off about worrying about it. There. And I'll comment on what this really means, adding this maximum index. Okay, so this is it. In one dimension, I've shown you that given any function, I can interpolate it sufficiently smoothly. In fact, this C3 was just an arbitrary choice in some sense. We could make it more regular, C4, C5, etc., by redefining the spline. Yeah, and this construction, by checking from the closed form for P sub k, you can verify that this coveted property holds. But I want to push this one step further. That was one-dimensional interpolation. And in reality, a lot of times we need multi-dimensional interpolation. Now, if we are going to redefine this polynomial now in the multi-dimensional setting, I might as well stop talking now, and we're all going to fall asleep, and it's going to be horrible and painful. Instead, what I'm really doing with the multidimensional setting, I want to show off another property of this interpolant, which will make it a lot more convenient for analysis purposes. Okay, so let's do this. To generalize the interpolation, to dimension more than one, it pays to think of P sub k, or even just simple P sub k of x, as the weighted sum. So this weighted sum representation is going to take us a long way. So P sub k, this is the sum. I goes from 0 to 4. Alpha times f of delta k plus I. And let me bring back the form of P sub k so that you believe me. Okay. So what are these alphas? We should think about this as basically a weighted sum of the value of the original function at 5 different grid points. I goes from 0 to 4. So right, this is f of k plus 1, f of k plus 2, plus 3, plus 4. And the weights here are just weights, okay? How do we, if we want to be rigorous and define these alphas or find out what they are, we have to go into the expression of the polynomial and read off or collect all the terms in terms of the value of the function, and then read off the weights there. So for example, what is the value of alpha k? This is I equals 0 of x. This corresponds to the weight of f of delta k. All right. So the weight assigned to f of delta k, here it's 1, here it's something, here it's something. It will take us expanding these forward differences, but we can recover the alphas from this P sub k expression. So my only point is that equivalently we can view P sub k as a weighted sum, right? And that's how I want you guys to think of it from now on. Okay. So using the weighted sum representation, it's a lot easier to generalize interpolating in multiple dimensions. Why? Well, basically, to interpolate a function that's defined on a multidimensional grid, I just want to interpolate along each dimension one at a time. So I'm going to apply the weighted sum representation along each dimension, and that's how I'm going to get my multi-dimensional interpolation. So given f, now from the multi-dimensional grid, let define k of x by k sub j of x is the leftmost grid point of that along that coordinate. And a sub f, this is the sum, the dimension goes from 0 to 4, alpha. So this is along the dth coordinate we're interpolating. And we're going to go all the way, the dth dimension, d minus first dimension, all the way to the first dimension. Let me move this. Alpha k sub 1 of x plus I sub 1, k sub 1 of x. Okay. And another convenient form for this is sum I1. If you're overwhelmed by this, and if you're thinking like, this is just too much and too quick for me right now, it's okay. I'm going to summarize all of the useful properties I want of the interpolant, and you will not need to think at this depth, okay? What I'm doing here is, again, really for the people who really want to know how it works, and that may not be you, that's okay. Plus sub j, x sub j, f of delta k of x plus I. Okay. Let me comment on the form. So first of all, from the top expression here, I hope you can see that all that I'm doing is applying a weighted sum across each dimension. Now, this f of delta k of x plus I. So what is going on here is, which values of the function am I relying on to construct the interpolant? Well, I'm always basing myself off the bottom left corner. Like this k of x is basically the bottom left corner of the slice corresponding to x. And I'm using the bottom left corner plus some extra coordinates to the right of it. And what is the I? I is a vector. And along each dimension of I, we're going to use from 0 to 4, those values. So for example, if I think about two-dimensional space, I don't even need these. 1, 2, 3, 4, 5, 6, 3, 4, 5. You kind of get the point. So if this is my value of x, this is where my k of x is going to be. Okay, well, delta k of x. And then I'm going to need to use 1, 2, 3, 4, 5 points to the right, 5 points above. Basically, I need to use the whole box. That's what's going on here. Cool. So just a reminder, this is just it's a weighted sum at the end of the day. And now let me summarize the properties. And this took me a while. Let us summarize the properties of AF of X that will be most useful. Okay, you think of this as the API. So, right, this is how the software, say, is implemented. This is the low-level stuff. But at the end of the day, you can get away without diving into that as long as you're using these four properties or this API. Call it property number one. The derivative AF of X is bounded by some constant that depends on the dimension times, so delta. Now, A is a multi-dimensional vector. So, right, the derivative, this is like the multi-dimensional derivative operator. So this is like the partial along the first coordinate, the partial along the second coordinate, the partial along the third coordinate, and then A defines the order of the partial derivative we take along each dimension. Okay, so for example, if A is 1, 1, then d2 dAf of X is partial along the first, partial along the second f of X. So that's just notation. Times the maximum from I goes from 0 for E minus A. E is the vector of all ones. And this is going to be norm delta A F delta sub K of X plus I. All right. So property number one is what I kept saying, this is what we're going to seek. That the derivative of the interpolated function can be bounded by the corresponding finite difference, but it's not just bounded by the corresponding finite difference at a single point. Basically, this says we have to look at a lot of different grid points and bound the corresponding finite difference there. Worst case, if we want to simplify notation, this is less than or equal to maximum 0 less than or equal to I less than or equal to 4 times E of delta A delta K of X plus I. But if you're in the case where these finite differences are just uniformly bounded, then the maximum, you don't need to worry about the maximum. And importantly, this holds for all X in RD as long as the order of the derivative is from 0 to 3. And for almost all X when the order of the derivative is equal to 4. Okay, so let me quickly comment why am I doing this? What's going on here? My original intention when coming up with this spline to interpolate things, I was going to say, well, I want to be able to carry out this generator expansion up to the fourth order term. Why the fourth order? Because last lecture we saw that if you work with a sufficiently high order expansion, then you can show that the rate of convergence is quicker. So we have a 1 over R versus 1 over square root of R rate of convergence. When I started out on this, I thought, okay, let me only make it C3, and that should be enough. In reality, I should have made P of X not a 7th order, But to make everyone's lives easier, I should have made it a ninth order polynomial, get this extra regularity. Then we wouldn't have to clarify all the time that it is only that this property holds only for the 0 to third derivative everywhere and almost everywhere in this case. So what am I saying? I'm saying if you're confused why there is this distinction, that was my mistake. I should have made the thing smoother. Okay, so that was kind of human error. Property number 2. Let me write it on the next page. Are there any questions about property number 1? No. Hopefully clear. Property number 2. Define this domain, all functions, such that for any x, y in Rd, we basically have this mean value theorem type result. Okay. So what is this? This is basically the class of functions. I'm missing an A somewhere. Yes, I'm missing. Oh, no, I'm not missing anything. This is a class of functions such that like the mean value theorem is satisfied. This is the derivative, the first derivative of the function everywhere from the leftmost endpoint to the rightmost endpoint of that box from x to y. Why am I doing this? Then d sub a f of x is in this function space for all a3. This would have been trivial. Okay. So what this is saying is basically any function that has a continuous derivative belongs to this state space. Okay. And if the interpolant was C4, we wouldn't need property number 2. But the problem is that the interpolant is not C4, but that's okay because its third derivative satisfies this mean value theorem type property. Okay, so effectively, this allows us to work with it as if it were C4. That was my point. That's a technical property. Property number 3, and this is important. This is a product rule. And the product rule here is given given 2 functions from the grid to the continuum, let H be the product of them. Then A applied to H is A applied to F multiplied A applied to G plus epsilon sub P. P stands for product. I'm going to carry this over to the next page. I need some more space. where epsilon sub p is at most some constant that depends on the dimension times the maximum, the first order stuff, okay. This is a symmetric statement. This one is pretty important. It basically, what we're going to do soon is we're going to forget what this interpolating operator capital A is. We don't care about its construction, and we're just going to be applying it to stuff. One property that satisfies is it's linear, and I'll come back to that. Another property or another useful thing, we're going to encounter a lot of cases where we have the product of two functions. And we're going to need to basically say, well, if we're interpolating the product of two functions, it's going to be the interpolant is going to be the product of the interpolants plus some error. And two comments here. One, if it helps, think of this term as just norm delta A G. Okay, that's if it helps. The reason I am not just simply bounding it by the norm is that a lot of the times these things are not bounded. They will grow. That's why I need these restrictions. Number two, the constant. This is in case anybody ever wants to track down or keep track of the constants. So in the world of Stein's method, this is a little bit of a detour, but there's a lot of value placed on having explicit constants and tracking them everywhere. Okay. And one time I was asked in the paper to please keep track of the constants. And so we went in and dug up everything, and we are keeping track of the constants. Now it turns out that when you start keeping track of the constants in this method, the constants are not flattering, to say the least. Dimension times 11404 to the power of d times 1595 to the power of d. Okay. So in other words, if you're ever in a setting where you need to apply the product rule, this error term epsilon grows at a ridiculous rate with respect to the dimension. But in particular, it's important that if in your setting the dimension is infinite, you can't do this. So the dimension has to be finite. Okay. And one last property. Property number 4. Suppose that I have a function and it is sufficiently differentiable. How sufficient? It has s minus 1 derivatives for some s between 1 and 4. And that dA is in this special domain where the mean value theorem works. When A is s minus 1. Then f of x let me write it down and then I will comment. So equal to some C times delta S times the maximum A S. Soup. And again, the constant for reference before. Okay, so what is this? Property number 4 is basically saying how close is my interpolated value to the original function. In other words, suppose that the original function wasn't just defined on a grid, but it was defined everywhere, and it was sufficiently smooth. Okay, we can think of s equals 4. If s is 4, and I have a C3 function such that dAf of x is in this special mean value theorem domain, then how well do I approximate this function with my interpolant? Well, the key here is that it's delta to the power of 4. So actually, the smoother the function, the tighter my error bound is going to be on it. It's delta to the power of s, and over here, it corresponds to the highest order derivative of the function that I can get. Put it another way, example, if f of x is a cubic polynomial, then a of f of x is just f of x. How do we see that? So if f is a cubic polynomial, the fourth order derivatives equal 0. And by putting in s equals 4 in this proposition, you get that the upper bound is actually 0. So you have perfect interpolation of the function. All this means to say is that the interpolant should approximate simple functions reasonably well, and this is the rigorous way to define it. Okay, and we're almost out of time, which is perfect. I want to give you the very last, maybe very quickly highlight it. What was the point that we do all of this? And that is to interpolate the Poisson equation. So I'm going to show this very quickly, and this is where I'm going to start from the next class. So if I take the Poisson equation minus h of x sub q is g f x of x sub q. Okay. Now I apply a to both sides. So on the left-hand side, a x is equal to a e h of x. How do we do that? How do we justify this? Well, this is just a constant. And by property number 4, which I just said, the interpolant is going to interpolate the constant. It's going to give you back a constant. Okay. So the value h of x minus minus sub q. This is basically going to equal, sorry, that if we apply to the left-hand side, we have a e h of x minus a h of x, okay? And then, let me leave it for next class, I'm going to show you that this basically equals the interpolant applied to the right-hand side. And this is a good place to stop. Okay, this is our end goal. With the help of this interpolating operator that we constructed, very painful, but we did it, we're going to be able to extend the Poisson equation to the entire continuum, and then some nice things are going to come out of that. Let me ask if there are any questions, and then I'll summarize very quickly what we did today, and then we'll be done. Okay, so to summarize, and I'm glad this all fit into one lecture because this is going to be the painful lecture. And if you're watching, number one, there's 14 pages here, the most important things are properties number 1 through 4. If you're looking at this or you're trying to study it after the fact, all I want you to realize is I have these 4 properties which act as an API to this concept of interpolation. Number 1, the derivatives of my interpolated function are bounded somehow by the corresponding finite differences of the original function. Number 2, I have basically the mean value theorem property satisfied by first, second, third order derivatives of the interpolant. Number 3, there's a product rule that goes on, and the error depends on the forward differences of the f and g functions. And number 4, if you're trying, the more smoothness that your function has, the smaller the error of interpolating it is going to be. And we have some error for interpolating arbitrarily smooth functions as well. The interpolant itself is necessary if you want to prove these properties. So if you're okay believing these, you don't want to understand the proof of these, you don't need to dive into the details or into the weeds that we discussed in the first half of the class here. Cool. Next class, we're going to apply this stuff. We're going to start from this expression. I'm going to develop it a little bit further, and we will see the benefit or the merit of going through all this pain in the first place. Okay. With that said, I'm done.